Imagine a vast cosmic web, not of galaxies, but of electricity. This is our power grid. It connects the immense energy of power plants to the tiny spark that charges your phone. For this journey to happen, electricity needs a guide, a shapeshifter. That shapeshifter is the power transformer. It is the unsung hero of our modern world. Without it, the entire system would collapse. It is the crucial link that makes long-distance power transmission not just possible, but efficient. It takes the raw, high-voltage power from its source and tames it, stepping it down for safe use in our homes, schools, and hospitals. It is the silent, humming heart of our electrified civilization, a testament to human ingenuity. Transformers perform their magic by changing voltage levels. Power is generated at a medium voltage, perhaps around 11 to 25 kilovolts. To send this power over hundreds of miles, we must minimize energy loss. The laws of physics tell us that loss is proportional to the square of the current. So, we use transformers to step up the voltage to extremely high levels, 220 kilovolts, 400 kilovolts, or even 765 kilovolts. This dramatically reduces the current, allowing electricity to travel vast distances with minimal waste. It's like sending water through a pipe. A higher pressure allows you to use a smaller pipe. High voltage is the high pressure of our electrical universe. At the other end of the journey, near our cities and towns, the process is reversed. Another set of transformers steps down the voltage. The 400 kilovolts from the transmission lines is reduced to a more manageable 66 kilovolts or 33 kilovolts for regional distribution. Then, smaller transformers near our neighborhoods lower it again to the 240 or 120 volts that power our lives. The size of these transformers, measured in megavolt amperes, reflects the amount of power they handle. A massive 500 MVA unit in a transmission substation is a galactic center of energy, while a small pole-mounted transformer is like a local star serving just a few homes. The basic construction of these giants is elegantly simple, rooted in Michael Faraday's discovery of electromagnetic induction. At its core, literally, it consists of two or more coils of insulated wire, called windings, wrapped around a shared magnetic iron core. There are no moving parts in the basic transformer, a beautiful example of physics in action. An alternating current in one coil, the primary winding, creates a changing magnetic field in the core. This magnetic field, a river of invisible force, then induces a voltage in the other coil, the secondary winding. The ratio of turns in the coils determines whether the voltage is stepped up or down. A simple principle, yet it powers our entire world. Let us journey into the heart of the transformer, to its magnetic core. This is where the energy conversion truly happens. The core is not just a solid block of iron, it is a carefully engineered structure built from thin sheets or laminations of a special material. This material is cold-rolled, grain-oriented silicon steel. The grain-oriented part is key. It means the magnetic domains within the steel are aligned in the direction of rolling. This alignment creates a superhighway for the magnetic flux, minimizing resistance and energy loss. Each lamination is only about 0.23 to 0.30 millimeters thick, a delicate sheet of engineered metal. These thin laminations are stacked together to form the limbs and yokes of the core. But why use thin sheets instead of a solid block? The answer lies in taming a pesky phenomenon called eddy currents. A changing magnetic field in a solid conductor induces swirling currents of electricity within it, like whirlpools in a river. These eddy currents do no useful work. They just generate heat, which is wasted energy. By slicing the core into thin, insulated laminations, we create barriers that break up these wasteful swirls. This simple yet brilliant solution dramatically improves the transformer's efficiency. ensuring that nearly all the energy makes it from one winding to the other. The geometry of the core is also a work of art. Modern transformers often use a step-lap core construction. Imagine stacking rectangular cards, but instead of aligning them perfectly, you stagger them at the corners. This is the essence of a step-lap joint. This overlapping design reduces the air gaps at the corners where the limbs and yokes meet. Air is a poor conductor of magnetism. By minimizing these gaps, we create a smoother, more continuous path for the magnetic flux. This further reduces magnetic losses and even quiets the characteristic hum of the transformer, a sound born from the vibrations of the core. Once the laminations are meticulously stacked, this massive, heavy structure must be held together with immense force. Steel channels, tie rods, and glass epoxy bands are used to clamp the core, turning it into a rigid, monolithic assembly. This clamping is critical. It prevents the laminations from vibrating, which would create noise and potentially damage the core over time. Insulation is also applied to the core's surface, separating it electrically from the windings and the clamping structure. This ensures that the only connection between the primary and secondary circuits is the invisible, magical dance of the magnetic field. Now, let's wrap our core in the conduits of power, the windings. These are the coils of copper or aluminum wire that carry the electrical current. In a power transformer, we typically find at least two sets. The low-voltage winding is made of thicker wire as it carries a higher current. The high-voltage winding, carrying a lower current at a higher potential, is made of thinner wire. Sometimes a third winding, called a tertiary winding, is included. It might be used to supply local power to the substation or to help stabilize voltages in the system. The arrangement of these windings is a matter of careful electrical and mechanical design. The placement of these coils around the core limb is not random. Typically, the low-voltage winding is placed closest to the core. Its lower voltage means it requires less insulation from the grounded core. The high-voltage winding is then wound concentrically over the low-voltage winding. This arrangement is mechanically strong and helps to control the immense electromagnetic forces that arise during a short circuit. These forces can be powerful enough to physically crush the windings if they are not designed and supported properly. The space between the windings is precisely controlled, filled with insulating barriers and oil ducts to ensure electrical integrity and allow for cooling. The windings conductors themselves are not bare metal. Each strand is coated with an enamel or wrapped in paper insulation. These individual strands are then wound together to form the complete coil. The primary insulation material used in oil-filled transformers is a special kind of paper, often called craft paper. This paper, derived from wood pulp, has excellent dielectric strength when impregnated with transformer oil. For structural support, and to create barriers between winding layers and sections, a denser material called pressboard is used. It is essentially a thick, rigid cardboard, also made from pure cellulose, designed to withstand electrical and mechanical stress. Different types of windings are used depending on the voltage and power rating. For lower voltages, simple helical or disc windings might be used. For the high-voltage windings of large power transformers, interleaved disc or continuous disc windings are common. These complex arrangements are designed to distribute voltage stresses evenly, especially during transient events like lightning strikes. The craft of winding a transformer is a blend of precision, engineering, and artistry, ensuring that these coils can withstand the electrical and mechanical forces they will endure for decades of service. It is a dance of copper, paper, and oil, choreographed by the laws of electromagnetism. A transformer's voltage ratio is determined by the number of turns in its windings. But what if we need to adjust that voltage? The load on the power grid is not constant. It fluctuates throughout the day and night. As demand changes, voltages across the network can sag or swell. To maintain a stable voltage supply for consumers, we need a way to fine-tune the transformer's ratio. This is the job of the tap changer. It is like a gearbox for the transformer, allowing us to change the number of active turns in a winding and thus adjust the output voltage. It is the active brain of the transformer, constantly making small adjustments. There are two main types, but the most sophisticated is the on-load tap changer, or OLTC. Its name tells you its most amazing feature. It can change taps while the transformer is energized and supplying load. It does this without interrupting the flow of power. You can't just break a circuit carrying thousands of amps. The resulting arc would be catastrophic. The OLTC performs this feat using a clever sequence of switches. It momentarily bridges the connection to the new tap before breaking the connection to the old one, using resistors or reactors to limit the massive currents that would otherwise flow during this brief transition. Inside the OLTC, we find two main components, the tap selector and the diverter switch. The tap selector is the slow part of the operation. It pre-selects the next physical tap on the winding that we want to move to. It does not carry or break any current itself. The real magic happens in the diverter switch. This is a high-speed, spring-loaded device that performs the actual current switching operation. When a tap change is initiated, the tap selector moves to the new position. Then, in a matter of milliseconds, the diverter switch rapidly transfers the load current from the old tap to the new one, using its transition resistors to ensure a smooth, arc-free handover. This ability to regulate voltage is absolutely critical for the stability of the power grid. The OLTC is usually connected to an automatic voltage regulator. This device continuously monitors the output voltage of the transformer. If the voltage deviates from a preset level, the AVR sends a command to the OLTC's motor drive to initiate a tap change, bringing the voltage back into the desired range. This automated system ensures that the lights in our homes stay bright and our sensitive electronics are protected from voltage fluctuations. The OLTC is a complex, beautiful piece of mechanical and electrical engineering, working tirelessly behind the scenes. A power transformer is, well, a world of extreme electrical stress. Hundreds of thousands of volts separate the windings from each other and from the grounded tank. Preventing a catastrophic flashover requires a robust insulation system. This system is actually a partnership between solid materials and a liquid dielectric. The solids, as we've seen, are the cellulose-based craft paper and pressboard that wrap the conductors and form barriers. But these materials alone are just not enough. Their true power is unlocked when they are completely impregnated with a special liquid transformer oil. This oil is, you could say, the lifeblood of the transformer. Transformer oil, typically a highly refined mineral oil, serves two vital functions. First, and most importantly, it is an excellent insulator. It permeates every microscopic void in the paper and pressboard insulation, displacing air and moisture. This combination of oil and cellulose actually has a much higher dielectric strength than either material alone. It fills all the gaps, preventing electrical discharges from initiating and creating a robust barrier against the immense voltage. It is the fluid medium that isolates the high-voltage components, allowing them to operate in close proximity without arcing over. The second crucial role of the oil is to act as a coolant. The core and windings of a transformer generate heat due to electrical losses. This heat must be removed to prevent the insulation from degrading and failing. The oil absorbs this heat from the hot windings and core. As the oil heats up, it becomes less dense and rises to the top of the tank. Cooler, denser oil from the bottom of the tank sinks to take its place. This natural convection, a process known as thermosiphon, creates a continuous circulation of oil. This moving river of oil carries the heat away from the core and windings to the tank walls and radiators, where it can be dissipated into the surrounding atmosphere. The purity of this insulation system is, honestly, paramount. Even tiny amounts of moisture or contaminants can drastically reduce the oil's dielectric strength and accelerate the aging of the paper insulation. Before a transformer is filled with oil, it undergoes a deep vacuum process in the factory. This removes air and moisture from the solid insulation. The oil itself is purified through a process of filtering, heating, and vacuum treatment to remove dissolved gases, water, and particulate matter. This meticulous preparation ensures the insulation system can withstand the electrical stresses and provide reliable service for many decades. It is a sealed, pristine internal universe designed for high-stress performance. How do we safely get the colossal power from the high-voltage windings inside the tank to the overhead lines outside? Well, we cannot simply run a wire through a hole in the steel tank. The immense voltage would instantly arc to the grounded metal, resulting in a violent failure. The solution is a specialized insulator called a bushing. A bushing is an insulated conductor that provides a safe passage for the current to travel through the grounded barrier of the transformer tank. It is the carefully guarded gateway between the transformer's internal world and the external grid. They are the elegant, often colossal, ceramic or composite pillars you see atop large transformers. For lower voltages, a simple solid porcelain insulator might suffice. But for high voltages, this is not enough. The electric field would concentrate at the sharp edges of the grounded tank opening, leading to breakdown. High-voltage bushings use a more sophisticated design, known as a condenser or capacitor-graded bushing. Inside the main porcelain or composite insulator, the conductor is surrounded by a series of concentric conducting layers, typically made of aluminum foil. These layers are separated by insulating paper. This structure acts like a series of capacitors, distributing the electric field smoothly and evenly along the length of the bushing, both internally and externally. This clever design prevents high concentrations of electrical stress at any single point, allowing the bushing to safely withstand hundreds of thousands of volts. The external part of the bushing, exposed to the air, has a series of sheds or skirts. These are not just for decoration. They increase the creepage distance, the shortest path for an electrical current to track along the surface of the insulator. In rainy or polluted conditions, a layer of contamination on the bushing surface can become conductive. The long, convoluted path created by the sheds prevents a flashover from occurring, ensuring reliability even in harsh weather. Bushings are mounted onto the transformer tank cover or sidewall. The high-voltage bushings are typically large and mounted on the top cover, while the low-voltage bushings, carrying higher current but at a lower voltage, might be side-mounted. The connection at the bottom of the bushing, inside the transformer, is made via a flexible lead to the winding. The top of the bushing has a terminal for connecting to the external bus bars or transmission lines. These components are among the most critical in a substation. A bushing failure can be explosive and lead to prolonged outages, so their design, manufacture, and maintenance are of the utmost importance. A power transformer is a highly efficient machine, but it's not perfect. Losses in the core and windings, though small in percentage, generate a significant amount of heat in a large MVA unit. A 500 MVA transformer might generate a megawatt of heat, enough to power a small neighborhood. This heat must be continuously removed. If the internal temperature gets too high, the paper insulation will rapidly degrade, drastically shortening the transformer's life. The cooling system is the transformer's radiator, its respiratory and circulatory system, designed to keep it operating at a safe temperature. The simplest cooling method is designated ONAN, which stands for oil natural, air natural. Here, the natural thermosiphon circulation of the oil, or oil natural, carries heat from the windings to the tank walls. The heat is then dissipated from the tank surface and from attached cooling radiators into the ambient air, purely by natural convection, or air natural. This passive system is reliable but has limited cooling capacity. It is suitable for smaller distribution transformers, or as the base rating for larger transformers. The radiators are simply a set of finned panels that provide a large surface area to help the heat escape. To increase the cooling capacity, we can add fans. This method is called ONAF, or oil natural air forced. The oil circulation is still by natural convection, but powerful fans are mounted below or beside the radiators. These fans blow a large volume of air across the radiator fins, forcibly convecting the heat away much more effectively than natural air movement. This allows the transformer to handle a higher load without overheating. An ONAF-rated transformer will have a base ONAN rating and a higher ONAF rating when the fans are running. The fans are typically controlled automatically by temperature sensors. For the largest and most powerful transformers, we need an even more aggressive cooling strategy. This is OFAF, or oil-forced, air-forced. In this system, we don't just rely on natural oil convection. We add oil pumps to the cooling circuit. These pumps actively force the oil to circulate from the tank through the radiators and back into the tank at a high flow rate. This forced oil circulation is far more effective at extracting heat from the windings. Combined with the forced air from the fans blowing on the radiators, the OFAF system provides the maximum cooling capacity, allowing the transformer to operate at its highest MVA rating. The transformer tank is more than just a steel box to hold everything. It is a robust, sealed vessel, designed to withstand internal pressure, the vacuum applied during processing, and the stresses of transport and operation for half a century. It's the protective shell for the delicate universe within. For large transformers, the tank is typically constructed from thick, welded steel plates, reinforced with stiffeners to prevent flexing. Its main purpose is to contain the core and coil assembly and the thousands of liters of insulating oil, protecting them from the external environment. Every opening for bushings, pipes, and instruments is carefully sealed with gaskets. Connected to the main tank, usually via a pipe, is a smaller cylindrical tank called the conservator. As the transformer heats up and cools down with changing load, the oil inside expands and contracts. The conservator tank provides the necessary space for this thermal expansion. It is only partially filled with oil, with the space above the oil connected to the outside atmosphere. This ensures the main tank remains completely full of oil at all times, preventing the hot core and windings from being exposed to air. Without a conservator, the pressure inside the sealed tank would fluctuate wildly, stressing the tank and its seals. But if the conservator is open to the atmosphere, doesn't that let in moisture and contaminants? Yes, and that is why we have a breather. The conservator breathes through a device filled with a desiccant, usually blue silica gel. As the transformer cools and oil contracts, it draws air in from the outside. This air must pass through the silica gel, which absorbs all the moisture. When the gel is saturated, it turns pink, signaling that it needs to be replaced or regenerated. This simple device is critical for maintaining the dryness and dielectric strength of the insulating oil. Between the main tank and the conservator lies a vital protective device, the Buchholz relay. This is a gas and oil-actuated relay installed in the connecting pipe. If a small incipient fault occurs inside the transformer, like a minor discharge, it will generate gas bubbles. These bubbles rise, travel up the pipe, and accumulate in the Buchholz relay, triggering an alarm. If a major fault occurs, the resulting surge of oil rushes through the pipe, tripping a second float in the relay, which sends a signal to immediately de-energize the transformer. Other key accessories include the pressure relief device, a spring-loaded valve that rapidly releases excess pressure, and various gauges to monitor oil temperature, winding temperature, and oil level. The journey of a power transformer from a customer's specification to a finished, tested product is a complex dance of engineering and documentation. This is the world of vendor engineering. It begins once a contract is awarded. The first and most important document produced is the general arrangement drawing. This is the master blueprint. It shows the overall dimensions of the transformer, the location of all key components like bushings, radiators, and the tap changer. It details the terminal arrangements, the total weight, and the transport dimensions. This drawing is the primary interface between the manufacturer, the customer, and the civil engineers designing the substation foundation. Following the general arrangement drawing, a cascade of detailed documentation begins. The bill of materials is created, listing every single component, from the tons of CRGO steel and copper down to the last nut and bolt. This is crucial for procurement and manufacturing. Simultaneously, engineers create detailed interface drawings. These include the foundation plan, showing the exact location and loading of support points. They create drawings for the high voltage and low voltage terminal connectors, ensuring they will match the customer's substation bus bars. Details of the control cabinet wiring, cable entry points, and marshalling kiosks are meticulously documented to ensure seamless integration on site. Each of these drawings goes through a rigorous review and approval process. The vendor submits them to the client's engineering team, who check them for compliance with the technical specification and for compatibility with their site design. This can involve several rounds of comments, revisions, and resubmissions. A key skill for a vendor engineer is managing this flow of information, responding to technical queries, and incorporating client feedback into the design. Clear, accurate, and timely communication is just as important as technical prowess. It is a collaborative process to ensure the final product is exactly what is needed. Once all the main drawings are approved, manufacturing can begin. But the engineering work is not over. During production, factory acceptance tests are performed. These tests, like ratio, winding resistance, insulation resistance, and complex impulse and heat run tests, verify that the transformer has been built correctly and meets all performance criteria. The vendor engineer prepares the test procedures and, after the tests are witnessed by the client, compiles the final test reports. This entire collection of approved drawings, test reports, and instruction manuals forms the final documentation package. It is the transformer's birth certificate, a complete record of its design, construction, and proven performance, ready for its long life at the heart of our electric universe.